for some of you it's quite late. So yeah, I'm Sasha Glavnyov, I'm from Georgetown University, and today I would like to talk about connections between data structures, circuit complexity, and cryptography. Please do feel free to ask questions anytime during the talk. Okay, yeah, let's start. So the motivating question behind this line of research is the following. Given a computational problem, we want to understand what computational resources are needed to solve this problem. So we want to understand how hard a problem is. But what is hardness? So there are several kind of dimensions to the hardness of a computational problem. First of all, of course, often we care about the time complexity of a problem. How much time we need to solve a problem, or what the most efficient algorithm for the problem. Yeah, but there are other resources where we might want to optimize as well, especially I say nowadays in the era of big data algorithms, we often want to find space efficient algorithms for a problem, right? We often want algorithms that say don't store even all of the input, or maybe don't even read all of the input. We need algorithms that have small space complexity. Yeah, obviously we all know that given a lot of reliable data, we can do some crazy things. And the bottleneck here often is that we don't have too much reliable data. So for many learning tasks, we might want to know how much reliable data, how much good data do I actually need to have to run my learning algorithms. So another resource to optimize is data, amount of data an algorithm requires. Another important resource is randomness. So say randomness is crucial for many problems, say for cryptography, the distributed computing, some efficient algorithms, but randomness is expensive. We can't just sample a ton of truly random bits. That's going to be super expensive. So we want to actually understand how much data and of what quality we actually need to perform some, say, security task. And these resources are studied in different areas of theoretical computer science. Say time complexity of a problem is studied in algorithms and circuit complexity, or we try to understand space complexity of a problem in communication complexity, in data structures, streaming algorithms. Machine learning or learning theory, they study the amount of data we need to solve a problem. And cryptography, among other things, studies the amount of and quality of randomness we need to perform certain tasks. And in the recent years, we have seen amazing connections between these seemingly unrelated areas. We learned how to get circuit lower bounds from learning. We learned how to do learning from cryptography. There are amazing, beautiful connections. And I guess it's fair to say that in the past years, my main research interest was in understanding and maybe developing these connections. So we have a bunch of fascinating connections between the different areas, and they're often quite fruitful. And today, my hope is to give you a gist of these connections. So the outline of today's talk is going to be the following. First, we'll talk about data structures. We'll see what data structures are, what we know about them, what we want to prove about them, how bad we are at what we want to prove. Then we'll see an equivalence. We'll show that actually the main question in data structures is exactly equivalent to an important question in cryptography. The connection will work in both ways. We'll see that given data structures, you can do cryptography and the other way around. And we'll use this connection in a funny way. We'll actually use a super old crypto trick that was used by hackers in the 80s to crack some passwords. We'll use it to refute a conjecture in geometry. We'll establish this connection and use it to use some hacker's trick to refute a conjecture in geometry. That's going to be fun. And after this, we'll see another connection. We'll prove that the main question, essentially the main question in circuit complexity is equivalent to the main question in data structure level bounds. Again, this connection will have some fun applications as well. So that's the outline of today's talk. First, we talk about data structures, see what we know about them. Then we'll see equivalence of data structures to cryptography and equivalence between data structures and circuit level bounds. All right, so any questions so far? Okay, so let me start then. Data structures. So we all know quite a few standard data structures, say all kinds of stacks, lists, queues, heaps, all kinds of search trees, hashing tables, hashing maps, blank filters, and so on. But today we're going to talk about data structures for slightly more involved problems. Okay, here's an example of such a problem: graph distances. I'm giving you a road network, the road network of all roads, say, in Russia. And it's kind of safe to assume that in the next, I don't know, 2 or 4 weeks, there will be no changes, no significant changes. So you essentially have like 4 weeks of time to preprocess this road network, which in nowadays essentially means that you have infinite amount of time to preprocess the road network. But once you are done preprocessing, I want you to efficiently answer my queries. My queries will be of the kind like, what's the shortest path from me to the library? And you quickly find the shortest path. Then I immediately give you a next query, like from the library, I want to go to a pub. What's the shortest path? You quickly answer this query. So there are 2 stages. In the preprocessing stage, you essentially spend as much time as you want, 4 weeks, to preprocess this given road network. But I want you to quickly, efficiently answer my queries. Shortest path between these 2 points, shortest path between these 2 points, and so on. Another problem of this kind would be the nearest neighbors problem. Here, for example, I can give you a bunch of points in the plane, or a bunch of cluster centers. Again, spend forever preprocessing them. But once you're done, please quickly, efficiently answer my queries. And my queries are of the form: I'm giving you a point in the plane, find the closest cluster center to it. Find the cluster it belongs to. And this is used by many machine learning algorithms for recommendations. Say Netflix, among other systems, uses this system for video recommendations. Again, this problem has 2 phases: preprocess this bunch of clusters and then quickly answer my queries. Or there is this range counting problem where I'm giving you a bunch of points in the plane, preprocess them, again, spend as much time as you want. But once I give you a query, and the query would be, say, a rectangle, count the number of points in this rectangle. I'm giving you another query, count the number of points in this rectangle, and so on. And this is used, say, by Amazon to estimate market size of certain segments. Okay, these are examples of data structure problems, and these problems are called static data structure problems because the input is static. The input is not going to change. You have forever to preprocess the input. So formally, not formally yet, but say in pictures, static data structure looks as follows. I'm giving you the static input. I'm giving you the road network of all say American networks. You preprocess it as long as you want. So and you give me a data structure, a bunch of zeros and ones. So think of this data structure as my Google Maps app. So I really don't care how much time some engineers in California spend preprocessing this road network. But once they have this data structure, once I have it in an app in my phone, I want it to quickly answer my queries. And queries are of the form like, what's the shortest path between, say, Washington and St. Petersburg? I want you to quickly look only at a few positions in a data structure and this data structure and quickly find the shortest path. I give you another query, what's the shortest path, what's the quickest way to get from Athens to Vilnius? You look at a few bits in the data structure and quickly give me the shortest path. So formally, a static data structure looks as follows. You have n inputs. Inputs are from some domain, maybe pick your favorite domain, maybe the field of 2 or anything else. Then you preprocess them, and you have unbounded computational resources to preprocess them into S memory cells. Again, each memory cell is from the same domain, maybe an element of F2. But then once you're done with this unbounded preprocessing, I want you to quickly answer my queries. There are n queries. You know them in advance as like all possible, say, pairs of cities, you know, all pairs of cities. And I want you to be able to answer each of the queries efficiently by looking only at a few memory cells and computing some simple function of this cells. So the query time is going to be T. Okay. So we typically think of data structures as data structures that have m, which is polynomial of n number of queries, the number of queries is usually polynomial in input size, maybe huge polynomial, maybe m is like n to the 100, but typically it's polynomial. This is reasonable in terms of our practical application. This also makes theoretical analysis simpler. So we usually think of m as like a huge polynomial in n. Okay, and in data structure, every data structure has two important parameters: how much space you use S, and your query time T, how much time you spend to answer a query. And we want to simultaneously optimize both of these parameters. We usually say that the data structure is efficient if it uses essentially minimal possible amount of space. So you need to store information about n input elements. So you need your space to be at least n. And if space is close to n, say n times polylog n, we say that's good, that's efficient. Similarly with query time, if your query time is polylog n or n to some tiny constant, tiny epsilon, then that's reasonable, efficient. Otherwise, the data structure might not be too efficient. Okay, any questions? Good. Let's see how we can solve data structure problems. Every data structure problem has two trivial solutions. Every problem can be always solved in the following two trivial ways. First, in my unbounded preprocessing stage, when I have as much time as I want, I can just pre-compute answers to all possible queries. I can compute them, store them in my data structure. Then, of course, my query time is just ideal. I already have an answer to all queries. But my space is just horrible, right? My data structure uses n to the 100 space, which clearly we don't want to use such data structures. Another trivial solution that works for every data structure problem is the following: just don't do preprocessing, just store the input in your data structure. So you're using the minimal possible amount of space, which is cool, but for any non-trivial data structure problem, the output will depend on all of the inputs. So your query time will be at least n. So the query time will be bad. This solution we don't want to use often either, because essentially you are not using data structure and you are not doing any preprocessing. You're just storing the input. So there are two trivial solutions. This one has good query time. This one has good space. And the field of data structures is about finding for what problems there are solutions in between, for which problems we can use better than trivial space and better than trivial time. Which data problems admit efficient data structures. All right, so it's quite easy to show that actually a random problem, that is, most problems are super hard for data structures. That is, if your space is slightly less than trivial, slightly less than n to the 100, then your query time must be trivial, like n, and the other way around. If your query time is just a tiny bit less than n, then your space must be like n to the 100. So most of the problems do not have anything in between. Most of the problems don't have any non-trivial data structure. But the challenge, as always, is to find an explicit problem that is hard. Give me an explicit problem like this. Graph distances problem or nearest neighbors. Give me an explicit problem that is hard. And we're not good at all in proving our data structure lower bounds for explicit problems. So the best lower bound we could prove for an explicit problem was proven in the 80s. It has the following form. And here recall that number of queries is typically like m is polynomial in n. So log m is essentially log n. So let me parse this bound for you. We have an explicit problem such that if your data structure uses essentially the minimum possible amount of space, just linear space, then yeah, query would require at least logarithmic time, while most of the problems would require actually linear time. We can only prove that there is a problem which would require like logarithmic time. And if your data structure uses slightly more than linear amount of space, slightly more than the trivial, like minimum possible amount of space, then we can't prove anything. We can only prove that T is at least constant. T is always at least constant. So that's how bad we are at proving data structure lower bounds. That's the current state of the art in data structure lower bounds. We'll pause here and we'll return this after we see some questions in cryptography. So now we'll switch to cryptography, and later we'll connect this problem of proving data structural error bounds to certain tasks in cryptography. That's an amazing place to ask a question.
What is the nature of the problem for which this lower bound is known?
Yeah, so that's a good question. For what problems can we prove at least this lower bound? Actually, there is a huge family of problems for which we can prove it. Essentially, any problem that has error correcting properties would do. For example, polynomial evaluation or multiplication by the Vandermonde matrix. When this is the Reed-Solomon error correcting code, it's at least that hard. Probably even harder, but we can prove it for this problem. But actually, over any field, take a reasonably good error correcting code, it would be that hard. Or take more generally, take any problem that is whose outputs are sufficiently independent, that has k-wise independent for k being like linear in n. You would still have this property. So yeah, we have a huge class of properties, essentially anything related to error correcting codes.
Okay, thank you.
Yep. All right, so we saw how bad we are at proving data structural error bounds. Now let's see how bad we are at cryptography. So we're going to be talking about cryptography with preprocessing. That's the following kind of cryptography. Yeah, for any interesting cryptography, we need hard functions. They're often called one-way functions, and this is the functions of the following form: functions that are easy to compute but hard to invert. And that's just the rule of thumb that you don't really design such a function yourself. I mean, if you come up with a function that looks hard to you and your buzzer couldn't invert it, that still chances are that one of the thousands of cryptanalytic techniques would break a function, would invert a function. So what we do instead is the following. People find hard functions, they publish them, then the whole crypto community tries to break these functions for years. If they don't succeed, then we take people who really know how to do it to implement these functions. Then again, the whole community tries to break them. If we didn't succeed in years, then we say, okay, this function might be reliable. We slowly start using it. So this process takes years. And the thing is that many of these functions were actually developed like in the 80s and the 80s and the 90s and 2000s. And back then, our computers were slow. So our n was small. We wanted these functions to be computed efficiently. So this n parameter was slow. Nowadays, when we have fast computers, we can actually even like brute force those functions in the following sense. We can preprocess this one-way function. The simplest way would be just take a computer which now has 2 to the n space, because back then n was small, and just store the inversion table. That is, for every output of the function, store a corresponding input. So store how to invert this function at every point. Nowadays, computers can even sometimes store the whole table, and then it's super easy to invert this function. We preprocess it, spend a lot of time and space on this but then we easily invert this function. And in fact, there is a class of attacks called rainbow table attacks that don't even require that much space and that much time. That they don't even require 2 to the n space. They can do it much faster. So many old functions can now be broken with this preprocessing. So what do? We can start the whole process.
So Sasha, hard functions here mean that they are not computable in polytime, right?
Right. Sorry, can you repeat the question?
Here, a hard function means a function which is not computable in polytime, right? Or
say it can be computed efficiently in polynomial time, but cannot be inverted in polynomial time.
Oh, okay.
Yeah. That's what say we mean by one-way function. But actually, what we want from one-way functions is even more. because what we want is the one-way function is published once and forever. It's going to be used for the next like 10 years. So in fact, I have 10 years to preprocess this function. And since it's still used after 10 years, if after 10 years of preprocessing I can break it, it's still not secure. So actually, we often want even more from one-way function. I want to say that it cannot be broken even with preprocessing.
Yeah. Okay. Yeah.
Yeah, and that would be fine, except that nowadays we can break with, we have enough computational power to preprocess old functions. So where do we get new functions that cannot be preprocessed and broken efficiently? One way is to start the whole process from the scratch, come up with a new function that is hard, show it to the whole crypto community, publish, test, and so on, but it's going to take years. What can we do instead? Ideally, we would like to have a simple immunization procedure. We say, okay, let me take an old function. It was secure, say, against computers with 2 to the n space, but no more. So how about I use that old function and amplify its hardness, and I construct a new function which is secure even against the modern computers, even against the computers with like 2 to the 5 n space. Clearly, my new function has to have longer input, longer output, but moreover, I want to prove that it's secure even against the modern computers. That would be an ideal solution, this immunization procedure that takes old function, somewhat secure against old computers, and just amplifies it into a new function, which is secure against modern fast computers. So this is what cryptography with preprocessing is. We don't know if such immunization procedure exists, but we recently showed that actually it exists if and only if one can prove data structure lower bounds for a certain class of problems. If you can prove that some problems are hard for data structures, we have this immunization procedure. If this immunization procedure exists, we can prove some data structure lower bounds. They're actually equivalent. The two questions are apparently equivalent. And here I'm talking about data structure lower bounds for a certain class of problems, but the class is supernatural. There are tons of cool problems, 3-sum, nearest neighbors, polygon containments, essentially all of computational geometry problems, not quite, but many of them. And instead of formally defining this class, I'll just show you an example of a problem from this class, and I'll show you a gist of this connection between cryptography and data structures, how these two fields can actually be connected. All right, questions? Yeah, I'm not sure if I see the chat. So if you have a question, it's better if you could unmute yourself and ask a question.
So,
all right.
What are you going to try? What are you going to show using these examples? It's not clear to me.
Yeah. So in general, we prove equivalence between data structure lower bounds and cryptography. I'm not going to show you this general equivalence. Instead, I'll show you how to use cryptography to solve data structure problems, which is like essentially one part of this connection. I'll show it on an example. I'll show you how to use cryptography to solve a specific data structure problem, to solve 3-sum, and refute the conjecture about hardness of this problem.
Okay.
So yeah, let me first define the 3-sum problem. 3-sum is an algorithmic version. The classical 3-sum problem is the following. I'm giving you n numbers, and just tell me if there is a triple among them AI, J, K, such that sum of the first two numbers is the third one. Given n numbers, check if there exists a triple like this. All right, that's a 3-sum problem. Even though it looks like a problem about numbers or like maybe combinatorial problem, it's actually the foundation of computational geometry. I mean, it's as hard as many problems in 2-dimensional computational geometry. There is a trivial algorithm that solves this problem in quadratic time, and there is a classical conjecture that says that actually you cannot do better. We don't know how to do better than n squared. Yeah, okay, a recent line of research said that, okay, if you just want to beat n squared, literally beat n squared, yeah, we can do something. We can shave off some polylog factor. We can do n squared or essentially log squared n. But okay, the modern three-sum conjecture says, yeah, maybe you can win some polylog factors, but you can't do better by a polynomial factor. You cannot even solve three-sum in time n to the 1.99. That's a big conjecture. We don't know how to prove it. We don't know how to refute it. Now let's look at the data structure version of this conjecture. Data structure version of three-sum is often called three-sum indexing, and the following problem. Again, I'm giving you numbers. Since this is a data structure problem, you are allowed to preprocess these numbers. So you store some as, say, numbers, as bits, whatever. And then after you're done with preprocessing, I want you to efficiently answer my queries. My queries are very simple. I'm giving you a number B, check if it's a pairwise sum of the inputs. If it's a sum of two inputs. Given such a data structure, you can solve the original three-sum problem, just, preprocess the numbers and then check if any of them is a sum of two numbers from the input. So this is a data structure version of the three-sum problem. How can we solve it? Okay, first of all, one solution would be I just, in the preprocessing stage, I compute all pairwise sums, so I can square of them, store them. And then during the query stage, when you give me a number B, I can do some binary search and see if it is a pairwise sum. So if I'm finally using quadratic space, then yes, there is an efficient data structure for this. And there is another trivial solution as always. You can just store the input, maybe sorted input, and then given a query, you can go kind of from two sides and figure out if it's a sum of two input elements in linear time. But again, the first solution kind of uses prohibitive space. The second solution uses prohibitively large query time. Would like to do better, but there is this conjecture that says that the moment when you are not in this region, the moment when you are using subquadratic space, you are immediately in this region. You have to use linear query time. The conjecture claimed that there is nothing in between. You're using subquadratic space, you must use linear query time. We are going to refute this conjecture right now using the connection between cryptography and data structures. We'll use a crypto trick to refute this conjecture. So we'll design a data structure for this problem with truly subquadratic space and truly sublinear query time. Good place for questions. All right.
Here you have assumed that this pre-processing time isn't included in T, right?
No. Preprocessing is unbounded, but okay, in fact, our data structure will be quite efficient. Its preprocessing will be done in time and square.
Yeah. Thank you.
All right, so we're going to use cryptography. Let me show you what kind of cryptography we're going to use for this. We're going to use a so-called function inversion primitive for this. The game here is as follows. Given a function from integers from 1 to n to integers from 1 to n, we want to preprocess the function f. So we want to store information about this function f, say as numbers, as bits. And then we want to efficiently invert f at any point. What does it mean? You give me y. I need to efficiently, I'm going to use my data structure to efficiently find x, which is mapped to y by this function f. So think of f as kind of one-way function. I'm allowed to preprocess it, store some information about it, some as bits, and then you give me an output. I want to invert it. I want to find the corresponding input to the function. And here, what does it mean? I want to do it efficiently. I want to invert it in some time t. That means I can look at t memory cells of this preprocessor data structure, or I can evaluate the function f t times. But yeah, the point is that I want to do kind of t operations, and I'm allowed to evaluate function f, of course. And in the 80s, Hellman and later Fiat and Nauer showed that in fact, there is a non-trivial algorithm, non-trivial data structure for this function. For example, you can always, for any function f, you can solve it with sublinear space and some linear time. And this algorithm is pretty simple. I'm going to show it to you. It's beautiful. I'll show it on this in the special case where function f is a bijection. That is, every number from 1 to capital N appears in the output of the function exactly once. For this case, we'll invert any such function actually with space and time square root of n. All right, so given a function which is a bijection, that is every number from 1 to n appears in the output exactly once, we want to preprocess it into space square root of n, such that at any point we can invert it in time square root of n. How do we do this? Okay, so we're going to draw a directed graph.
It's a stupid question probably, but still, if you have function is of size n, how can you squeeze it into square root of n bits? For information reasons, it should be impossible.
Absolutely.
The inverse function have the same number.
Absolutely. So the good point Sasha has is that if you have n essentially bits of information and you preprocess them into square root of n bits of information, you lost information about the function. You cannot invert it. Yeah, but once again, in my query, I'm allowed to do T operations, which are reading the memory cells, which is not sufficient by Sasha's argument, but I'm also allowed to query the function f. So I do have all the.
Do you have an access to an oracle for a function unlimited?
Right, right.
Yeah, sorry.
For example, if t is n, if I am allowed to make n capital N queries to the function f, I just can query it at all points. Yeah, but we want to do better, and in fact, we will do better. We'll do s and t being like square root of n right now. Yeah, good point. Thank you. Okay, so how do we do this? We define a directed graph. Vertices will be just all numbers from 1 to capital N, and I'll draw edges, directed edges, from x to f of x. For every number x from 1 to n, I just draw one directed edge from x to f of x. That's my graph. So what's the out degree of a vertex in this graph? There is exactly one edge from every vertex, from every x. It goes to f of x. So out degree of every vertex is exactly 1. But also recall that the function is bijection, that is, every number appears in the output exactly once. So every vertex has exactly one incoming edge as well. I have a directed graph where all in degrees and out degrees are exactly 1. What does such a graph look like? You can just traverse it, you'll get to the original point. So it's just a bunch of directed cycles, just a union of directed cycles. That's what my graph is. Now let me look at one of this cycles. Okay, I pick any vertex there. Say I mark it with this ginger cross, and I say you're going to be my landmark. That's a landmark vertex. Now I skip the next square root of n vertices, and I say this next one is my next landmark. Skip another square root of n, another landmark, and so on. I keep going like this. Okay. Now I'm going to store all the landmarks, all the orange crosses. And for each of them, I'm also going to store a link to the previous landmark. Those orange links to the previous landmarks. That's all what I store. I only store landmarks, and for every landmark, also a link to the previous one. So how much space do I use? Once I store a vertex, I skip square root of n vertices. I store one, skip square root of n, one, square root of n. So I store at most square root of n vertices. So my space is good. I'm indeed using square root of n space. Is there a question?
Yeah. And for short cycles, you don't store anything, yeah?
Yeah. If a cycle is even shorter than square root of n, I just ignore it. Mikhail, did you have a question too?
It was my question about short cycles.
Yeah. I just ignore them actually. Yeah, good question. So yeah, I proved that my space is square root of n at most, but let me show you how to invert every function at every point in time square root of n. So what does it mean to invert? You give me some y, which is f of x, and I need to find x. So y is some point in my graph. And recall the definition of the graph. I have arcs from x to f of x. So x is the previous vertex in this cycle. Given this y, I want to find the previous vertex in the cycle. So I start here. What can I do? I can evaluate the function f at this point y. What does it do? Right, exactly by the definition of the graph, I just make a step along the cycle. All edges are from y to f of y. I just go to the next vertex in the cycle. I evaluate f again. It gets me here. I see that, oh, that's my landmark. So I have a link to the previous landmark. Let me check it out. I go there and I keep evaluating the function f until I reach this point x. That's it. I found x. I just inverted f. How many steps did I make? Well, that's the length of this arc. And the length of each arc is at most square root of n. So indeed, in times square root of n, I just inverted the function. That's it. That's the whole algorithm. It works for bijections here, but it can be generalized with slightly worse parameters. It can be generalized to every function f. We can invert every function f with non-trivial parameters, and essentially the same way. I hear a question, I guess. No.
So you more or less say that if all cycles are short, you can just go along the cycles until you come back.
Exactly.
And if not all are short, you are just changing the permutation a bit and make all cycles short and then keep the difference.
Exactly.
That's what you're saying.
Yep.
No, in a big circle, how many such cycles are there? I'm a bit confused.
It might be one or it might be n. Yeah.
In here, like you have formed like 5 semicircles, right? So if it's like and each semicircle is of root n size.
Mm-hmm.
So if it's not constant many number of semicircles, then it's going to be a problem, right? Because then the space would also not be root n. You need, how can you guarantee that it's constant number of?
Yeah, I never use it. It's like constant number or something. The space is always at most square root of n, and it's easy to see in the following way. Once I store a landmark, whatever the length of the cycle is, in any case, I'm gonna skip the next square root of n vertices. So I always store, if I store a vertex, I skip square root of n vertices. So at most, I can store only square root of n vertices, n over square root of n.
Oh,
Yeah. Yeah, here it doesn't matter how long the cycles are. Just for short cycles, I just don't store anything because I don't really need to. If the cycle is of length 5, I just evaluate function f like 4 or 5 times and get the pre-image. I just go along the cycle.
Okay.
So in this case, time is, you are allowed in the time you have, you're allowed to read the entire process table. So
in this specific case, that's true, but in general, this would work if S was like n to the 2/3 and C would be n to the 1/3. Then you wouldn't be able to read the whole thing, but you actually don't need to do it. Oh, you mean in the preprocessing stage?
No. But with 2/3, you need some other construction, or you do the cycles.
In the same construction here, I never actually use that S and C as square root of n. I could have skipped n to the 2/3 vertices, or I could have skipped n to the 1/3 vertices. The algorithm would be the same. It works for every S and C whose product is n. So, for example,
but then you need to, when you go along the cycle, you need to check whether you are in this cross place.
Right.
So you need to check
just
against all landmarks.
Yeah, store landmarks in a sorted way and use some efficient binary search to check if your current vertex is stored.
Yeah.
Mm-hmm. All right. So that's how we invert bijection. We can actually invert any function with non-trivial parameters, but we're going to use it to solve the three-sum problem. Let's do this. So let me remind you, three-sum problem in this data structure world is the following. I'm giving you n numbers, preprocess them, and now that I give you a query b, number b, check if it's a pairwise sum of inputs or not. Okay, let's solve this problem. How do we do this? Let me define a super simple, silly function. F of 2 indices, each index is from 1 to n. F of I and j is just the sum of 2 corresponding input numbers. F of I and j is ai plus aj. Yes, silly, but let's see what properties this function has. First of all, f is super easy to compute. There is nothing to compute. You take two numbers, sum them up. Okay, what's the domain of this function? How many different inputs it takes? Well, there are n values for I, n values for j, so there are n square possible inputs to this function. What's the range of this function? In principle, yeah, these numbers, a's, they can be large, so the range can be large, but look, the output of this function is always a pairwise sum of the inputs, and there are n square pairwise sums. So you can always hash down these numbers to integers from like 1 to 10n square. Just because there are n square pairwise sums and you only care about pairwise sums, you can always hash down the original numbers to numbers from 1 to say 10n square. So without loss of generality, you can actually assume that the range of the function is also of size n square. Both the domain and range have size n square. And finally, the main property is that if you invert f, you solve 3-sum. The 3-sum is exactly this problem. I'm giving you a number b. Is there a pair of indices I and j such that ai plus aj equals b? All what I need to solve the 3-sum problem is to invert this function f. And now we know that we can actually invert every function f in some non-trivial way. What do we need to invert the function? Recall that while we're going along the edges of the path, we keep evaluating the function f. So we want f to be easy to compute. Yeah, it's super easy to compute here, just sum up two numbers. What else do we care about? The only parameter in this function inversion procedure was the capital N, the size of the domain and the size of the range. And we have it like pretty reasonable. It's pretty small here, just n squared. So if we just plug in these parameters in this function inversion procedure, we see that we can invert this function with any space and time that satisfies the following equation: s cubed times t is n to the 6th. In particular, I can pick truly subquadratic s and truly sublinear t. In particular, I can solve 3-sum in subquadratic space and sublinear time, refuting the previous conjecture.
But you assume that f was bijective, right? In the previous case,
No,
here.
yeah. So as I said here, we can invert every function quite efficiently with these parameters that I actually just used for 3-sum, but I just showed you a simpler version of inversion of bijection. But we can actually invert every function with these parameters. And since our capital N is little n squared, we have data structure with exactly these parameters. Okay.
N raised to 6 was the bound over there.
Say it again.
N raised to 6 was the bound over there. Yeah,
right. Yeah. So we're not using function inversion for bijections. We're using function inversion for general functions, which are not necessarily bijections. All right. So that's how we use, say, cryptography to do data structures. But in fact, this connection is deeper apparently, and it works in the other direction as well. For example, if you could prove interesting data structural lower bounds, you can use it for immunization procedure. For example, if 3-sum is hard, here are 3 lines of code that take an old, weak one-way function and construct a provably strong new one-way function. That's the simplest example. You can do better things, but I'm just saying that it's like if you can prove data structural lower bound for problems like 3-sum or polygon containment or something, then you get cryptography with preprocessing, and the other way around. So what we need strong data structural lower bounds. We actually proved a data structural lower bound for the 3-sum problem and related problems. It matches the best known data structural lower bounds for any problem, but it's still too weak for reasonable cryptography. For reasonable cryptography, we want even stronger data structural lower bounds, but apparently there is a barrier. And the barrier lies in a different field. It lies in the field of circuit complexity. So in the remaining maybe 5 minutes, if that's fine, I'll just quickly explain how this barrier may look like, why we're stuck at this weak data structural lower bounds. So there is this beautiful field of circuit complexity. The game here is as follows. You want to compute a function, say, from n bits to n bits. What you can do is you use straight line program. That is, you use any binary operations of previously computed things, but you don't have any branchings. You don't have if statements, you don't have loops, just have a program where which you evaluate line by line. You can always draw such a program as a directed acyclic graph. It's also called a circuit. So that's what a circuit for a function looks like. Formally, you have an input variables, some constants. You can compute any binary functions in the gates. And again, we know that a random function, almost all functions require circuits of exponential size actually 2 to the n. But if we could find an explicit function which is hard, not even exponentially hard, just super polynomially hard, say from the class NP, then we would prove that P is not equal to NP. It would resolve the biggest problem in complexity. But currently, the best what we can actually prove is just a lower bound of roughly 3n, even for programs from a much larger class. Actually, it's 3.1n, and it was proven 2 months ago by Lee and Young. So we know most functions have exponential complexity. We would like to prove just super polynomial. The best we can do is like 3n. That's the state of the art in this area. And so the first step would be to prove any superlinear circuit lower bound. And we have tons of candidates. We have many natural functions that we believe should require superlinear circuits. We just don't have tools to prove such circuit lower bounds. But for circuits of with one more natural restriction of logarithmic depth, BOOLEAN in the 70s gave us a way that potentially can prove superlinear circuit lower bounds. He said that if you can compute a function by a linear size circuit, say of logarithmic depth, then you can also compute it by the following depth to circuit. You take an inputs, you preprocess them into epsilon n memory cells, and now you compute every output by looking only at a few inputs and a few memory cells. So if you find a function that cannot be computed by this, by this depth to circuit, then you prove a superlinear circuit lower bound finally. But look, I just want to say that, look, the top picture, we see efficient data structure. The bottom picture, we see efficient circuit by valence reduction. The pictures look somewhat similar. There are some differences, like circuit has fewer than n memory cells, but data structure has more than n memory cells. Circuit can look at inputs and memory cells. Data structure can look only at memory cells, but they still look similar. We'd love to say that these two pictures are equivalent, but we don't know how to do this. In a recent work, though, a couple of years ago, we proved that for linear problems, these two pictures are equivalent. If you're computing a linear function, that is a function which where every output is a linear combination of the inputs, then apparently these two pictures are equivalent. And there are many natural linear problems for which we're proving lower bounds. And yeah, that's the main message in that result. So we cannot improve data structure lower bounds. So we said for cryptography, we need better data structure lower bounds. And the best data structure lower bound we proved in the 80s. And apparently, if you improve it for any regime of space, for any regime of time, you would get a better circuit lower bounds, which is another notoriously difficult problem in complexity, with which we are stuck like for some 40, 50 years or so. So this is some explanation why we're so bad at proving data structure lower bounds. Or maybe that's an explanation why we're so bad at proving circuit lower bounds. Apparently, these two questions are equivalent. We've been studying them in two different areas for years, just using different notation, but they are the same question. All right, that's it for today. Please let me know if you have any questions.
Yeah, thank you very much. Questions?
You stop recording, maybe.
Yeah, sorry. Just you said that there are no explicit problems with which are hard in terms of data structures.
That's correct.
You mean that even if we assume, for example, the existence of one-wave function, it doesn't help to show that there are some, doesn't help to prove for specific function that it's hard. Or you mean that we don't know this result?
No, I mean unconditionally. Conditionally, of course, we have data structure lower bounds. No, I mean unconditionally, we don't have good.
So you have conditional lower bounds for specific data structures.
Right. For specific data structure problems, yes.
And this is different with the circuits or not?
No. The circuit is the same thing. If you assume that I have one-way function, yeah, then like a non-uniform one-way function, yeah, then of course we'll have super polynomial circuit lower bounds. But we want to prove unconditional lower bounds, both in data structures and in circuits. And we don't know.
Yeah.
Conditionally, we have. Other questions?